Welcome back. So, we will continue the discussion on the heat equation, rather the semi group generated by the heat equation. So, let me just recall what we have done in the last two classes. So, this is del u by del t got to Laplacian u. Okay. So, this we define this semi group W t f is just k t star f and W 0 f is f. So, here f is in LPRN. So, this is T positive. And so, we showed that this WT is a strongly continuous contraction semigroup. So, the general theory tells, general theory and what further did important generator. Generator we should A so is given by Laplacian y for f in what we denoted by this d Laplacian p. So, this is set of all f in LP such that its distributional Laplacian is also in LP. So, the general theory then tells, so because this is a contraction semigroup, general theory implies that this lambda positive is contained in the resolvent set of A, and we have the resolvent estimate lambda A less than or equal to lambda inverse for all lambda positive. So, you also can see that. So, again what is connection with heat equation. So, now you put u of x t is equal to W t f at x. So, this is for t positive and x in R n. Because of the smooth character of this k t, the Gaussian, so you immediately see that even though f is only in LP, okay, just remember that f is in LP, okay. This implies that u is a smooth function of x, smooth function of x and t positive, okay. And you can easily verify that, and u of t is Laplacian. So, u indeed satisfies this heat equation in T positive. This is important, okay. This, though f is only an LP function and the initial condition is satisfied, initial condition is satisfied in the limit sense. So, this is T minus f in LP tends to 0 as t tends to 0. Of course, the general semigroup theory tells you that if the initial condition is in the domain of the generator, then we have classical solution, but here because of the smooth kernel, that namely the Gaussian, we do have even for general f in LP. Okay, so that's so this is an example of the holomorphic semigroup I was talking about, though I did not define that, but you can read and understand. So, this semigroup generated by the heat equation is indeed an holomorphic semigroup. Now, the question is again comparing with the abstract Cauchy problem. So, how can we assert? So, now the converse. Okay, so some interesting things happen here. So, in fact, we do not know the complete answer. So, now you start with this abstract heat equation, okay, and just compare this with du by dt equal to au. Okay. So, we know that if A generates a semigroup, then we have a solution of this abstract Cauchy problem. So, here our operator A is Laplacian. Okay. So, Laplacian, consider the Laplacian. So, just by looking at this Laplace operator on appropriate domain, we want to verify the conditions of Hille-Yoshida theorem and conclude that there is indeed a semigroup generated by Laplacian. Okay. And this is not that easy. So, I will just make some remarks. Consider the operator Laplacian on d delta. So, this is a subspace of LP and this is the maximum possible domain where the Laplacian can be defined. Okay. So, the easier part, so you can easily verify that Laplacian is a linear closed densely defined operator. This is not hard, but you should do that, defined operator. Okay. The hard part is the spectrum. Spectrum or resolvent. Okay. So, remember in the direct problem where we started with the semi group and showed that Laplacian is the generator. So, this resolvent condition was obtained, and also this is from the general theory. So, if you try to prove these conditions, so we should prove, okay, that is the, at least let us write what we should prove. Okay. We need to show that the set lambda greater than 0, the positive real line is in the resolvent set of Laplacian, and not only that, and this R lambda Laplacian. So, let me write that, what that is. So, lambda I minus Laplacian inverse is less than or equal to lambda inverse. So, in effect we need to solve, in order to at least attempt to show these things, need to solve first of all this equation lambda I minus Laplacian. So, let me put F. So, for a given G, so G, this is G in LP, right, LP Rn. Okay. So, for every G in LP, we should be able to find an F in the domain of delta, that is d Laplacian P, satisfying this equation. Okay. And remember, there are no initial or boundary conditions, anything, only this class, this F has to belong to this domain. Okay. And that gives you the uniqueness. We want uniqueness, then only that inverse can be defined, and then we have to obtain this norm estimate. Okay. For p equal to 2, we can rely on Fourier transform, and show this, show the existence, uniqueness, etc. Okay. And for p not equal to 2, it is not even clear how to proceed. How to proceed. And this is where we find some gaps in the text. So, generally you find most of the books dealing only with L2 theory, that is P equal to 2 theory, but very few books on LP theory, and they are also scattered. Okay. So, there is a strong need for the unification of all these results and then application to partial differential equations. Okay. So, before I mention a reference for this, so even if you take n equal to 1, this is interesting. Okay. So, then we get an ODE. Okay. So, in this case we have to solve f equal to g. So, this is in LPR now. Okay. I am taking n equal to 1. Okay. And even this is not very straightforward, and this is left as an exercise. So, in fact, since this is a linear equation with constant coefficients, only thing is now we are taking the inhomogeneous term in LP, and you show that you can write down a formula for the solution, and you also see that solution is unique, though we have not mentioned any initial condition or conditions at infinity here. Okay. So, even n equal to 1, it is not very straightforward. So, you have to, though it is an ODE, you do it. Okay. And in the direct problem, of course, we can also use this Laplace transform of the semi group in order to represent this. Okay, this here itself I write. Okay, here. So, R lambda A can be written as Laplace transform of W. Okay, so, these are hard, even formulas are very hard, because this computing Laplace transform is not at all easy, because this kt involves. So, Laplace transform is with respect to t variable. So, you have to integrate with t, and there are t terms in the denominator. So, that is not easy. Okay, so general LP. So, there is a book by Martin Chester. So, he has many books, but this one is titled Solving Linear PD. And there is a subtitle, spectra. Okay, so, this is published by World Scientific. So, this is 2020. So, very recent, very recent. Because same author had written many years back again a book titled Spectra of Linear PD. I do not know whether it is kind of reproduction or whatever, but anyhow we have the latest book on that. So, there some LP theory is discussed. So, let me just make a remark of that. So, P not necessarily 2. Okay. So, there he introduces, let me just write that. So, species. So, these are, at least I find these species are somewhat new. Okay. HSP, S a real number, and for the definition we can take even infinity, no problem. So, these are similar to HS space. We learned via Fourier transform when p equal to 2. Okay. So, these are also similar to that. Okay. So, for u in the, so these are all in Rn. Okay. So, these spaces are considered in Rn. Let me not write that everywhere. So, u is in S. Okay. So, define. So, just recall when p equal to 2 what we did, we took the Fourier transform and then multiplied by a polynomial factor and again then took L2 norm. Okay. Similar to that. Okay. So, S is a better space because we can operate Fourier transform, and the inverse Fourier transform is also in the same space. So, you take first, so u SP. Okay. So, you take Fourier transform, let me use that Fu, and then you multiply by this 1 plus mod chi square. Yes, I put directly yes. Yes or yes. Okay, let me just put yes now. Or yes by 2. I will check that. And again, so this is in S, and you are multiplying which has C infinity function, which has a growth at most of a polynomial. So, again that is in S, and now I take the inverse Fourier transform, that is also in S. Okay. And now you take the LP now. When p is equal to 2, there is no need to take the Fourier inverse, because the Plancherel theorem will help us, or that relation we have, that L2 norm of a function is equal to L2 norm of its Fourier transform. Okay. So, when since p may not be 2, so we have to take again this. So, observe that this entire thing is again in S, that is important. Okay. And this HSP is the completion of S in this norm. And then one can derive using in this space. Okay. This completion is, I will you do not get a clear picture of the space in general, because they are only equivalence classes. So, this is one among them. So, we know it is a Banach space, etc., etc., but a clear description of the elements in HSP is not known. So, we will have few more such spaces, but we can still work with them. Okay. Just being a general Banach space, we can do that. Okay. So, in Martin Schester's book, so we can get finally this our aim of this. So, we do get an answer for this thing. So, we can do show, and then we can also obtain conditions on the resolvent, and then we can apply the semi group theory. Okay. So, that is one thing. Just what else I have? Fine. This is again those estimates, of course, are not at all easy. So, they use some more technical tools. Okay. So, let me just mention that more technical tools. So, you really enter hard analysis. Okay. So, this Cauldron, Zygmunt type estimates, LP multipliers, so since only specialists keep working in such areas, so it is difficult to give a overview of these things, but there is lot to do. Okay, that is my finally message, that so when we go from p equal to 2 case to p not equal to 2, the things become very very hard, very hard. Okay. So, with that I now move on to just okay, the next topic is just wave equation. Okay. So, here also you see some surprises. Okay. So, this is second order equation. Let me begin with that and then I will continue. So, again I work in Rn, okay, and then second order equation. So, we just so let me use now is not u. Let me see what I have used something. Okay, because this we are going to use the same notation. So, f1x f2x, okay, x in Rn. Okay. So, let me begin with some classical theory and some classical estimates, and then we move on to the semi group theory. So, let me just so if so the first thing, so you can assume this f1 and f2 are in the Schwarz space, RC in okay. So, we again want to use the Fourier transform technique to write down the solution. So, use Fourier transform to write down the solution. So, let me just write that and we will continue. So, let me write that u x t 2 pi. Again this constant depends on what Fourier transform we use. So, just write here e to the I x dot j cosine of, these are coming from solving the ordinary differential equation after taking the partial Fourier transform with respect to x variable. So, T mod j f1 cap j plus sin T mod j by mod j f2 cap j dj. Okay. So, it is indeed difficult to unwind this expression for f1 cap in terms of f2 cap. That is so for the expression in terms of f1 and f2, you can look into our books. Okay. Look into our PDE book. So, that is of course, we do not use Fourier transform there, we do it directly, but it should be similar. Okay. That is the advantage here is, so this since f1 and are in Schwarz class, so are their Fourier transform. So this is a, in fact you get a C infinity function here. So u is C infinity. Okay. So I will just continue with one more classical result, and then we will go to the semi group theory. Thank you.